Okay, so what you have studied in your mathematics course is given a periodic function fx, you can write it as sum of cosine plus sum of sine, isn't it? Plus there is a constant term. Okay, and sometimes this constant term is absorbed in this summation over this cosine. Now tell me, what are these cosine terms? What is inside this bracket? Suppose this is having a fundamental period t naught. Then what about these cosine terms? It is summation over, let's say I am writing it as k from 1 to infinity. Is it something like this? Cos, then what is inside that bracket? Okay, I am writing it as 2 pi by t naught. I am summing over k. So it is it this? N is the summation that here I am summing over k. So this is 2 pi kx plus sine. So what about that? That is also 2 pi by t naught kx plus there is a constant term. Sorry, it is not the form. There is scaling factor, isn't it? I am writing it as some bk and ck. There are some constants. It is linear combination of sine and cosine, not sum of sine and cosine. Is it? There are some coefficients here. So this is the form of Fourier series representation you have studied. So since in signals and system study we consider function xt. Okay, this is xt is used to represent signals. Suppose if xt is a periodic signal having fundamental period t naught, then we can express it as xt is a signal having fundamental period t naught. We can express it as there is a constant term. I am writing it as b naught plus. So this is a function of t. So I am writing it as cos 2 pi by t naught kt plus summation from 1 to infinity, and next is summation k sine 2 pi by t naught kt, isn't it? Sorry, there are some coefficients. This I am writing it as bk and this is ck. This is the form of Fourier series representation you have already studied, and this is called the trigonometric Fourier series. We are expressing a periodic signal having fundamental period t naught as a sum of a constant term plus sum of cosine, linear combination of I can say linear combination of a combination of cosine signals and linear combination of sine waves, isn't it? Sine and cosine. Now what is this 2 pi by t naught? What is 2 pi by t naught? T naught is the fundamental period of the signal. What is 2 pi by t naught? It is the fundamental frequency omega naught. So in terms of this fundamental frequency, let us write it as xt is equal to b naught by 2 plus summation over k from 1 to infinity bk cos omega naught. Okay, let me write it as k omega naught t plus summation over k ck sine k omega naught t, isn't it? This is the Fourier trigonometric Fourier series representation. Okay. Now we in this course we consider a different form of Fourier series representation that is called the exponential Fourier series representation. I will derive that formula for that exponential Fourier series from this. Okay, before deriving that, let me tell you a few things. Suppose we have let's say I am considering a periodic signal like this. This is a periodic signal. Okay. This is a period. Okay, let me write it in a new page. This is not scroll it. Okay. So this is a periodic signal. Okay. This is a periodic signal. I have drawn a few periods of that signal. So this is one period of the signal, isn't it? From here to here. So this is T naught. There is a constant term. Now, what is when this is summation k from 1 to infinity? Now, what is the signal corresponding to k equals 1? It is a cosine signal having what is the fundamental period of that signal? When k is 1, it is the term is b1 cos omega naught t, isn't it? K is 1. Now, what is that? It is a sine, it is a cosine signal of this is let's say this is the period, so this is the signal, isn't it? It is scaled by b1. Okay, it is a cosine signal having the same period as the signal xt. Now, what about the second term when k is 2? Is it like this? This is a cosine signal having double the frequency of this. And if we keep on doing that, when for some value of k, what is the frequency of that cosine signal? It is k times the fundamental frequency of the. Now, what about the second term in the summation? Second in that Fourier series expansion, second summation. It is same. Only difference is that now it is a sine wave. Here it is cosine, so it is sine wave having different frequencies, multiples of that omega naught. So that is a Fourier series representation, and you must have studied in your mathematics course. This is called the first harmonic. The signal having fundamental frequency k times omega naught, that is called the kth harmonic. Okay, kth harmonic means its fundamental the frequency of that signal is k times the fundamental frequency omega naught. That is called the kth harmonic. Okay, so in Fourier series representation, what we do is express a periodic signal as a linear combination, as a constant term plus linear combination of cosine signals plus linear combination of sinusoidal signal, sine waves, isn't it? Okay, now starting from, I have mentioned that this is not the form of Fourier series that we will be using in this course. We'll be using exponential Fourier series representation. So I will derive that exponential Fourier series from this trigonometric Fourier. This is called trigonometric Fourier series. Okay, now if I am writing this as, okay, I can write xt as b naught by 2 plus I'm writing cos omega naught t as e to the power j k omega naught t plus e to the power minus j k omega naught t by 2 plus by 2j. Now I am combining the terms containing e to the power j k omega naught t. So we can write it as b naught by 2 plus summation k from 1 to infinity commas bk minus. Is it that? I am taking the terms containing these two terms, combining these two. So it is bk plus there is 1 by 2j. So if you if you write it, we can write it as bk minus jck by 2. Is it okay? plus, what is the next term, next summation? 1 to infinity bk, what? bk plus jck by 2 e to the power minus jk omega naught t, isn't it? Now can I write this as this second summation, this as summation from k minus infinity to minus 1 b minus k plus j c minus k by 2 e to the power j k omega naught t, this term, this summation. I'm replacing k with minus k. Okay, now we can combine all these summations. We can write it as from minus infinity to infinity e raised to j k omega naught t. Can we write like this? This summation is from minus infinity to minus 1. This is from 1 to infinity. There is a constant term. Now tell me, what are these coefficients ak? How are they related to bk and ck? What is a0? A0 is B0 by 2. You equate the terms here. It's like first if you equate this is when k is 0, this is constant. So if you equate the constant terms on both sides, you will get A0 is equal to B0 by 2. Now what is AK for k greater than for k greater than 0? That is for positive values of k. What is AK? Is it this summation? For positive values k from 1 to infinity. So these are the coefficients in that summation. So are they same as this for k greater than 0? So k greater than 0, we can write it as ak is equal to bk minus jck. Is it? Sorry, by 2. Now what about k less than 0? ak is equal to what? Equate these two. For k less than 0, it is not bk, it is b minus k. Okay, here we have changed the variable from k to minus k to make it e to the power j k omega naught t. So here it is minus k, minus k. So it is b minus k plus j c minus k by 2. Okay. So what we have shown here is, let me summarize it. If we have a periodic signal xt in the trigonometric Fourier series expansion, this is the trigonometric Fourier series representation. And what we have just now what we derived is, this can be written as k from minus infinity to infinity this is another form of Fourier series representation, and this is called the exponential Fourier series. Okay, this is called the exponential Fourier series representation, and both are Fourier series representation different forms. This is trigonometric Fourier series representation in terms of sine and cosine. Here it is in terms of complex exponentials. This is called exponential Fourier series representation. We'll be using this exponential Fourier series representation. First, let me explain you the reason why we consider this complex exponential, this exponential form of Fourier series representation. Okay. Before that, suppose if we consider a signal xt, if xt is real valued, if we consider a real valued signal xt, what about these coefficients bk, ck, b0? They are real valued or Are they real valued? Hello? They are real valued, isn't it? They are real valued signals because if xt is real valued on both sides, imaginary part must be 0. So all these are real valued signals. Now what about this? These coefficients ak? Are they real valued? Not necessarily. That is an important difference because if when you say ak, we have seen that a0 is b0 by 2, and for k greater than 0, ak is bk minus jck by 2, and k less than 0, it is ak is bk, uh, sorry, b minus k plus jc minus k by 2. Okay, so here because of this ak, even if xt is real, it is not necessary that ak are real. Some cases it will be real, we'll discuss that later on. But here, for a real valued signal, all these coefficients are always real valued. Okay, these are called the Fourier series coefficients, bk and ck. And here, this ak is called exponential Fourier series coefficients. Okay, Fourier series coefficients.